What is data analysis? Data analysis is a systematic process of inspecting, cleansing, transforming, and modeling data with the goal of discovering useful information, informing conclusions, and supporting decision-making. It involves various techniques and processes to extract insights from raw data, making it more understandable and actionable. This field combines elements of statistics, computer science, and business intelligence to solve complex problems. Effective data analysis can uncover hidden patterns, correlations, and trends that might not be immediately apparent. It is a critical skill in nearly every industry today, driving innovation and strategic planning. Understanding data analysis is fundamental for anyone looking to make data-driven decisions. The primary goal of data analysis is to extract valuable insights that can be used to improve processes, predict future outcomes, or optimize performance. It helps organizations understand their customers better, identify market opportunities, and mitigate risks. By converting raw data into meaningful information, data analysis empowers stakeholders to make informed choices. This process is iterative, often requiring analysts to revisit earlier steps as new insights emerge or data quality issues are identified. Ultimately, data analysis transforms raw numbers into a compelling narrative that guides action. Importance of data analysis. Data analysis plays a pivotal role in modern business and scientific research by providing a factual basis for strategic decisions. It enables organizations to move beyond intuition and make choices grounded in evidence, leading to improved efficiency and profitability. For instance, businesses use data analysis to understand customer behavior, optimize marketing campaigns, and forecast sales trends. In healthcare, it helps identify disease patterns, evaluate treatment effectiveness, and manage public health initiatives. The ability to analyze data effectively is a competitive advantage, allowing companies to innovate faster and respond to market changes more adeptly. It empowers individuals and organizations to gain a deeper understanding of complex phenomena. Beyond business, data analysis is crucial in fields like environmental science for climate modeling, in social sciences for understanding societal trends, and in sports for performance optimization. It helps identify root causes of problems, predict future outcomes, and personalize experiences for users. Without robust data analysis, organizations risk making costly mistakes, missing critical opportunities, and failing to adapt to evolving landscapes. Therefore, mastering data analysis is not just a technical skill, but a strategic imperative for navigating the complexities of the 21st century. Types of data analysis. Data analysis can be broadly categorized into several types, each serving a distinct purpose in the analytical process. Descriptive analysis focuses on summarizing historical data to understand what happened. This involves calculating averages, frequencies, and other measures to describe the main features of a dataset. Diagnostic analysis delves deeper to understand why something happened, often involving techniques like drill down, data discovery, and data mining to identify root causes. These two types form the foundation for understanding past events and their underlying reasons. They are crucial for initial exploration and problem identification within any dataset. Predictive analysis aims to determine what is likely to happen in the future, using statistical models and machine learning algorithms to forecast trends and probabilities. This type is essential for risk assessment, sales forecasting, and strategic planning. Prescriptive analysis goes a step further by suggesting what action should be taken to achieve a desired outcome, often leveraging optimization and simulation techniques. This is the most advanced form of analysis, providing actionable recommendations. Each type builds upon the previous one, offering increasingly sophisticated insights and guidance for decision-making. Data analysis lifecycle. The data analysis lifecycle is a structured process that guides analysts from raw data to actionable insights. It typically begins with defining the problem or objective, clearly outlining what questions need to be answered and what goals need to be achieved. This initial phase is crucial for ensuring that the subsequent analysis is focused and relevant. Once the problem is defined, the next step involves data collection. Gathering relevant information from various sources. This might include databases, APIs, web scraping, or surveys, ensuring the data is appropriate for the defined objective. Careful planning in these early stages prevents wasted effort later on. Following collection, data cleaning and preprocessing are essential steps to ensure data quality and prepare it for analysis. This involves handling missing values, correcting errors, removing duplicates, and transforming data into a suitable format. Exploratory data analysis, EDA, then allows analysts to understand the data's main characteristics, identify patterns, and detect anomalies through visualization and descriptive statistics. After EDA, modeling and analysis techniques are applied to build predictive or prescriptive models. Finally, the insights gained are communicated through reports, dashboards, or presentations, enabling stakeholders to make informed decisions. This iterative cycle often requires revisiting earlier steps as new information or challenges arise. Sources of data. Data can originate from a vast array of sources, both internal and external to an organization. Internal sources typically include transactional databases, CRM systems, ERP systems, and operational logs, which capture day-to-day business activities. These sources provide valuable insights into customer interactions, sales performance, inventory levels, and operational efficiency. Understanding and accessing internal data is often the first step in any analytical project. The quality and accessibility of internal data are critical for effective analysis, as it forms the core of many business intelligence initiatives. Organizations invest heavily in systems that generate and store this proprietary information. External data sources expand the analytical possibilities by providing context and broader market intelligence. These can include publicly available datasets from government agencies, research institutions, and open data portals. Social media platforms, web scraping, and third-party data providers also offer rich external data. Examples include demographic data, economic indicators, weather patterns, and competitor activity. Combining internal and external data often leads to more comprehensive and powerful insights, allowing for a holistic view of the environment. The challenge lies in integrating these diverse sources effectively for analysis. Data collection methods. Effective data collection is fundamental to any successful data analysis project, ensuring that the acquired data is relevant, accurate, and sufficient for the analytical objectives. One common method involves surveys and questionnaires, which gather primary data directly from individuals through structured questions. These can be administered online, via phone, or in person, allowing for both quantitative and qualitative insights. Designing clear, unbiased questions is critical for obtaining reliable responses. The choice of survey method often depends on the target audience and the type of information sought. Proper sampling techniques are also essential to ensure representativeness. Another crucial method is observation, where data is collected by directly watching and recording behaviors, events, or phenomena in their natural settings. This can be done manually or through automated systems like sensors and cameras, providing objective insights into real-world processes. Experiments involve manipulating one or more variables to determine their effect on an outcome, often used in scientific research and A/B testing. Lastly, utilizing existing databases and archives, known as secondary data collection, involves accessing data that has already been collected by others. Each method has its strengths and weaknesses, and the best approach often involves a combination tailored to the specific research question. Data acquisition techniques. Data acquisition techniques refer to the specific tools and processes used to extract or retrieve data from its sources. One common technique is using application programming interfaces, APIs, which allow different software systems to communicate and exchange data seamlessly. Many web services, social media platforms, and financial institutions offer APIs for programmatic data access, enabling automated and real-time data retrieval. Understanding how to interact with APIs is a crucial skill for modern data analysts. This method ensures structured and efficient data transfer, reducing manual effort and potential errors. APIs are particularly valuable for integrating data from various online services. Web scraping is another powerful technique involving the automated extraction of data from websites. This is often used when no official API is available, allowing analysts to gather information like product prices, reviews, or news articles. However, it requires careful adherence to website terms of service and legal considerations. Database queries, primarily using SQL, structured query language, are fundamental for retrieving data from relational databases. Extract, transform, load, ETL processes are also vital for moving data from source systems, cleaning and transforming it, and loading it into a data warehouse or data lake for analysis. Each technique requires specific technical skills and careful planning to ensure data integrity and efficiency. Ethical considerations in data collection. Ethical considerations are paramount in data collection, ensuring that data is gathered responsibly, respectfully, and legally. Privacy is a core concern, requiring strict adherence to regulations like GDPR and CCPA, which govern how personal data is collected, stored, and processed. Obtaining informed consent from individuals before collecting their data is a fundamental ethical principle, ensuring they understand what data is being collected and how it will be used. Anonymization and pseudonymization techniques are often employed to protect individual identities while still allowing for valuable analysis. Organizations must prioritize data security to prevent unauthorized access and breaches, safeguarding sensitive information. Bias in data collection is another critical ethical challenge. If data collection methods or sources are inherently biased, the resulting analysis and decisions can perpetuate or amplify existing inequalities. For example, biased sampling can lead to skewed insights that do not accurately represent the population. Transparency about data collection practices and data usage is essential for building trust with individuals and the public. Accountability for data handling and the potential impact of data-driven decisions is also a key ethical responsibility. Adhering to these principles is not only a legal requirement, but also crucial for maintaining public trust and ensuring fair and equitable outcomes from data analysis. Data quality issues. Data quality is paramount for reliable analysis. Poor quality data can lead to inaccurate insights and flawed decisions. Several common issues plague datasets, significantly impacting their utility. Incompleteness refers to missing values in critical fields, which can arise from data entry errors, system failures, or non-responses in surveys. Inaccurate data contains incorrect or erroneous entries, often due to human error, faulty sensors, or outdated information. These issues directly compromise the integrity of any analysis performed. Identifying and addressing incompleteness and inaccuracy early in the process is vital for maintaining data trustworthiness. Inconsistency occurs when the same data is stored in different formats or with conflicting values across various systems or records. For example, a customer's address might be spelled differently in two separate databases. Duplication refers to redundant records, where the same entity appears multiple times, skewing counts and analyses. Untimeliness means the data is outdated and no longer relevant for current decision-making. Lastly, invalidity arises when data does not conform to defined rules or constraints, such as an age field containing a negative number. Addressing these issues through rigorous data cleaning and validation processes is essential to ensure the reliability and effectiveness of data analysis. Data cleaning techniques. Data cleaning is a crucial step in the data analysis pipeline, aimed at improving data quality by identifying and correcting errors, inconsistencies, and missing values. One fundamental technique is handling missing data, which can involve imputation, filling in missing values with estimated ones, such as the mean, median, or mode, or deletion, removing rows or columns with too many missing values. The choice depends on the extent of missingness and the nature of the data. Another technique is dealing with outliers, which are data points significantly different from others. Outliers can be removed, transformed, or treated using robust statistical methods, depending on whether they represent legitimate extreme values or data entry errors. Correcting structural errors is also vital, such as inconsistent capitalization, misspellings, or different representations of the same entity, e.g. USA versus United States of America. This often involves standardization and normalization processes. Removing duplicates is straightforward but essential to prevent skewed analyses. This can be done by identifying and deleting identical records. Data validation rules are applied to ensure data conforms to predefined constraints, flagging or correcting invalid entries. Regular expressions can be used for pattern matching and extraction. These techniques, often performed using programming languages like Python or R, are iterative and require careful consideration to avoid introducing new biases or losing valuable information. Data transformation. Data transformation is the process of converting data from one format or structure into another, often necessary to make it suitable for analysis or to integrate it with other datasets. This step typically occurs after data cleaning and before modeling. One common transformation is normalization, which scales numerical data to a standard range, for example, 0 to 1 or -1 to 1. This is particularly important for algorithms sensitive to the magnitude of values, such as those used in machine learning. Standardization, another scaling technique, transforms data to have a mean of 0 and a standard deviation of 1, useful for comparing variables on different scales. Aggregation involves summarizing data, such as calculating sums, averages, or counts for groups of records. This reduces the granularity of data and can reveal higher-level patterns. Discretization or binning converts continuous numerical data into categorical bins, simplifying the data and sometimes improving model performance. Feature engineering, a more advanced transformation, involves creating new variables from existing ones to improve the predictive power of models. Examples include combining two columns or extracting components from a date. These transformations are critical for preparing data for specific analytical tasks and enhancing the interpretability of results. Handling missing values. Missing values are a common problem in real-world datasets and must be addressed appropriately to avoid biased or inaccurate analysis. One primary approach is deletion, where rows, records, or columns, features containing missing values are removed. Row-wise deletion, also known as list-wise deletion, is simple but can lead to significant data loss if many records have missing data, potentially reducing the sample size and statistical power. Column-wise deletion is suitable if a variable has too many missing values to be useful, but it means losing an entire feature. These methods are generally used when the amount of missing data is small or when the missingness is completely at random. Imputation is a more sophisticated approach that involves filling in missing values with estimated ones. Common imputation techniques include replacing missing numerical values with the mean, median, or mode of the respective column. For categorical data, the mode is frequently used. More advanced methods include regression imputation, where a regression model predicts missing values based on other variables, and k-nearest neighbors (KNN) imputation, which uses the values from the k nearest data points. Multiple imputation creates several complete datasets by imputing missing values multiple times, accounting for the uncertainty of the imputations. The choice of imputation method depends on the nature of the data, the extent of missingness, and the underlying assumptions about why the data is missing. Introduction to Exploratory Data Analysis (EDA). Exploratory data analysis (EDA) is a critical initial step in the data analysis process, focusing on understanding the main characteristics of a dataset, often with visual methods. It involves summarizing the data's properties, identifying patterns, detecting anomalies, and testing hypotheses. EDA helps analysts gain insights into the data's structure, distribution, and relationships between variables before formal modeling. It is a detective-like process where the analyst probes the data to uncover its secrets. This phase is crucial for formulating appropriate questions and selecting suitable analytical techniques. EDA provides a foundation for more advanced statistical analysis and machine learning. The primary goal of EDA is to get a feel for the data, to see what it can tell us beyond the formal modeling or hypothesis testing. It helps in identifying potential problems with the data, such as outliers or missing values, and suggests ways to clean and transform it. Through various graphical and statistical techniques, EDA allows analysts to confirm assumptions or discover unexpected relationships. This iterative process often involves generating plots, calculating summary statistics, and asking insightful questions about the data. Effective EDA can significantly improve the quality and reliability of subsequent analytical steps, leading to more robust conclusions. Descriptive statistics. Descriptive statistics are fundamental tools in exploratory data analysis (EDA), used to summarize and describe the main features of a dataset. They provide simple summaries about the sample and the measures, forming the basis of virtually every quantitative analysis of data. Measures of central tendency, such as the mean, median, and mode, describe the typical or central value of a dataset. The mean is the average. The median is the middle value when data is ordered, and the mode is the most frequent value. These measures help in understanding where the data points tend to cluster. They offer a quick snapshot of the average behavior within the data. Measures of variability, or dispersion, describe how spread out the data points are. The range is the difference between the highest and lowest values, providing a simple measure of spread. The variance and standard deviation quantify the average squared difference and average difference, respectively, from the mean, offering more robust insights into data spread. The interquartile range, IQR, describes the spread of the middle 50% of the data, useful for identifying outliers. Skewness measures the asymmetry of the data distribution, while kurtosis describes the tailedness or peakedness of the distribution. Together, these descriptive statistics provide a comprehensive overview of a dataset's characteristics, enabling analysts to quickly grasp its essential properties. Data visualization for EDA. Data visualization is an indispensable component of exploratory data analysis (EDA), transforming raw data into graphical representations that reveal patterns, trends, and anomalies more effectively than raw numbers. Visualizations allow analysts to quickly grasp complex relationships and distributions, making it easier to identify insights and communicate findings. Common visualization types include histograms, which show the distribution of a single numerical variable, and bar charts, used for comparing categorical data. These basic charts provide immediate insights into the frequency and magnitude of different data points, forming the bedrock of visual data exploration. Scatter plots are excellent for examining the relationship between two numerical variables, revealing correlations or clusters. Vine charts are ideal for displaying trends over time, showing how a variable changes across a continuous period. Box plots effectively summarize the distribution of a numerical variable and highlight outliers, useful for comparing distributions across different categories. Heat maps display relationships between two categorical variables or show intensity across a grid. Effective data visualization is not just about creating pretty pictures. It's about conveying information clearly and accurately, enabling deeper understanding and facilitating data-driven decision-making. Choosing the right chart type for the data and the question being asked is crucial. Identifying patterns and anomalies. Identifying patterns and anomalies is a core objective of exploratory data analysis, EDA, providing crucial insights into the underlying structure and unusual occurrences within a dataset. Patterns refer to recurring relationships, trends, or groupings that suggest a systematic behavior in the data. These can be linear trends in time series data, clusters in customer segmentation, or correlations between different variables. Recognizing patterns helps analysts build predictive models and understand the normal functioning of a system. Visualizations like scatter plots, line graphs, and heat maps are particularly effective for pattern detection. Understanding these regularities is key to making informed predictions. Anomalies, also known as outliers or exceptions, are data points that deviate significantly from the majority of the data or from expected patterns. They can represent errors in data collection, rare events, or genuinely unusual behaviors that warrant further investigation. Detecting anomalies is critical in various applications, such as fraud detection, network intrusion detection, and identifying manufacturing defects. Techniques like box plots, z-scores, and more advanced clustering algorithms can help pinpoint these unusual observations. Distinguishing between legitimate anomalies and data errors is crucial, as both require different responses. Identifying both patterns and anomalies allows for a comprehensive understanding of the data's behavior and potential areas of interest. Probability and distributions. Probability is a fundamental concept in statistics and data analysis, quantifying the likelihood of an event occurring. It ranges from 0, impossible, to 1, certainty, and forms the basis for inferential statistics, allowing us to make predictions and draw conclusions about a population based on a sample. Understanding probability helps in assessing risk, making informed decisions under uncertainty, and interpreting the significance of analytical results. Key concepts include independent and dependent events, conditional probability, and the law of large numbers. These principles are essential for building robust statistical models and understanding their limitations. Probability distributions describe the possible values a random variable can take and how often they occur. Common distributions include the normal Gaussian distribution, characterized by its bell-shaped curve, which is central to many statistical tests due to the central limit theorem. The binomial distribution models the number of successes in a fixed number of independent Bernoulli trials, while the Poisson distribution models the number of events occurring in a fixed interval of time or space. Understanding these distributions is crucial for selecting appropriate statistical tests, constructing confidence intervals, and performing hypothesis testing. Each distribution has unique properties and assumptions that dictate its applicability in data analysis. Hypothesis testing. Hypothesis testing is a formal statistical procedure used to make inferences about a population based on sample data. It involves formulating two competing statements: the null hypothesis, H0, which typically states there is no effect or no difference, and the alternative hypothesis, H1 or Ha, which states there is an effect or a difference. The goal is to determine whether there is enough evidence in the sample data to reject the null hypothesis in favor of the alternative. This structured approach helps in validating claims, comparing groups, and assessing the effectiveness of interventions. It provides a rigorous framework for drawing conclusions from data. The process of hypothesis testing involves several steps. First, stating the null and alternative hypotheses. Second, choosing a significance level, alpha, typically 0.05, which represents the probability of rejecting the null hypothesis when it is actually true, type 1 error. Third, calculating a test statistic from the sample data. Fourth, determining the p-value, which is the probability of observing data as extreme as, or more extreme than, the sample data. Assuming the null hypothesis is true. If the p-value is less than alpha, the null hypothesis is rejected. Finally, a conclusion is drawn in the context of the problem. Common tests include t-tests, ANOVA, and chi-squared tests, each suited for different types of data and research questions. Regression analysis basics. Regression analysis is a powerful statistical method used to model the relationship between a dependent variable and one or more independent variables. Its primary goal is to predict the value of the dependent variable based on the values of the independent variables. Simple linear regression, the most basic form, models the relationship between two continuous variables using a straight line. This line, known as the regression line or line of best fit, minimizes the sum of squared differences between the observed and predicted values. Understanding this fundamental concept is crucial for predicting outcomes and identifying key drivers. The output of a regression analysis typically includes coefficients for each independent variable, indicating the strength and direction of their relationship with the dependent variable. The R-squared value measures the proportion of the variance in the dependent variable that can be explained by the independent variables, indicating the model's goodness of fit. Assumptions of linear regression include linearity, independence of errors, homoscedasticity, constant variance of errors, and normality of errors. Violations of these assumptions can lead to unreliable results. Multiple linear regression extends this concept to include more than one independent variable, allowing for more complex and realistic modeling of real-world phenomena. Regression analysis is widely used in economics, finance, marketing, and many scientific fields for forecasting and understanding relationships. Correlation analysis. Correlation analysis is a statistical method used to evaluate the strength and direction of a linear relationship between two quantitative variables. Unlike regression, which models cause and effect or predictive relationships, correlation simply measures how closely two variables move together. The most common measure is Pearson's correlation coefficient, R, which ranges from -1 to +1. A value of +1 indicates a perfect positive linear relationship, -1 indicates a perfect negative linear relationship, and 0 indicates no linear relationship. Understanding correlation is essential for identifying variables that tend to change in tandem, which can be useful for feature selection or understanding underlying dynamics. It is crucial to remember that correlation does not imply causation. Just because two variables are correlated does not mean one causes the other. There might be a third confounding variable, or the relationship could be coincidental. Visualizing correlations through scatter plots is highly effective, allowing analysts to quickly observe the pattern of relationship. Other correlation measures, like Spearman's rank correlation, are used for nonlinear relationships or ordinal data. Correlation analysis provides valuable insights into the interdependence of variables, guiding further investigation and model building. It helps in simplifying complex datasets by identifying redundant variables or those that move together. Spreadsheets for data analysis, Excel. Spreadsheet software, particularly Microsoft Excel, remains a widely used and accessible tool for data analysis, especially for smaller datasets and initial explorations. Its intuitive grid-based interface allows users to organize, store, and manipulate data effectively. Excel offers a rich set of built-in functions for performing calculations, statistical analysis, and data aggregation. Functions like sum, average, count, and various statistical functions enable quick summaries and basic descriptive analysis. Its ease of use makes it a popular choice for business users and those new to data analysis, providing a low barrier to entry for many analytical tasks. Beyond basic functions, Excel provides powerful features like pivot tables and pivot charts, which allow for dynamic summarization and visualization of data, enabling users to quickly identify trends and patterns across different categories. Data validation tools help maintain data quality, while conditional formatting can highlight important data points. Excel's what-if analysis tools, such as Goal-Seek and Scenario Manager, support decision-making by exploring different outcomes. While not suitable for very large datasets or complex machine learning, Excel is an invaluable tool for data cleaning, basic statistical analysis, reporting, and creating simple dashboards, serving as a foundational skill for any aspiring data analyst. Programming languages, Python, R. For more advanced and scalable data analysis, programming languages like Python and R are indispensable. Python, with its vast ecosystem of libraries, such as pandas for data manipulation, NumPy for numerical computing, and scikit-learn for machine learning, has become a dominant language in data science. Its readability, versatility, and strong community support make it an excellent choice for everything from data cleaning and transformation to complex statistical modeling and automation. Python's integration capabilities also allow it to connect with databases, web services, and other applications seamlessly. It is widely used across industries for its flexibility and power. R is another powerful language specifically designed for statistical computing and graphics. It boasts an extensive collection of packages, example Diploma for data manipulation, ggplot2 for visualization, and numerous packages for specific statistical models that cater to a wide range of statistical analyses. R excels in statistical modeling, hypothesis testing, and creating high-quality data visualizations, while Python is often favored for general-purpose programming and production deployment. R remains a strong choice for statisticians and researchers who require deep statistical capabilities. Both languages offer unparalleled flexibility and power compared to spreadsheets, enabling analysts to handle large datasets, perform complex analyses, and build sophisticated data-driven applications. SQL for data retrieval. Structured query language, SQL, is the standard language for managing and manipulating relational databases, making it an essential skill for any data analyst. SQL allows users to retrieve, insert, update, and delete data, forming the backbone of data acquisition from many enterprise systems. Analysts primarily use SQL's select statements to query databases and extract specific information needed for analysis. This involves specifying which columns to retrieve, which tables to join, and what conditions to apply for filtering rows. Proficiency in SQL ensures efficient and precise data extraction from large, structured datasets. Beyond basic select statements, SQL offers powerful capabilities for data aggregation, example using group by with aggregate functions like count, sum, average, sorting, order by, and filtering, where, having. Analysts can join multiple tables using various join types, inner join, left join, etc., to combine related information from different parts of a database. Subqueries and common table expressions, CTEs, enable more complex data manipulation and organization. Understanding SQL is crucial for accessing and preparing data from relational databases, which are ubiquitous in business environments. It provides a robust and standardized way to interact with data, ensuring data integrity and consistency across different platforms. Business intelligence tools. Business intelligence (BI) tools are software applications designed to collect, process, analyze, and visualize large volumes of data to help organizations make better business decisions. These tools bridge the gap between raw data and actionable insights, making complex data accessible to a wider audience, including non-technical stakeholders. Popular BI tools include Tableau, Power BI, and ClickSense, each offering robust capabilities for data integration, dashboard creation, and interactive reporting. They enable users to explore data visually, identify trends, and monitor key performance indicators, KPIs, in real time. The primary benefit of BI tools is their ability to transform data into understandable and actionable business intelligence quickly. Key features of BI tools include data connectors that link to various data sources, powerful data modeling capabilities to prepare data for analysis, and intuitive drag-and-drop interfaces for creating interactive dashboards and reports. These dashboards often feature a variety of visualizations, such as bar charts, line graphs, pie charts, and geographical maps, allowing users to drill down into details and customize their views. BI tools significantly reduce the time and effort required to generate reports and analyses, empowering business users to self-serve their data needs. They are crucial for operational monitoring, strategic planning, and performance management, providing a holistic view of business health and opportunities. Storytelling with data. Storytelling with data is the art of crafting a compelling narrative around data insights to effectively communicate findings and drive action. It goes beyond simply presenting charts and numbers. It involves structuring information in a way that resonates with the audience, making complex data understandable and memorable. A good data story has a clear beginning, the context or problem, a middle, the analysis and insights, and an end, the recommendations or call to action. This approach helps bridge the gap between technical analysis and business understanding, ensuring that insights are not just seen, but truly understood and acted upon. It transforms raw data into a persuasive argument. Key elements of effective data storytelling include understanding your audience, identifying the core message, choosing appropriate visualizations, and using clear, concise language. The narrative should highlight the most important insights, explain their significance, and provide actionable recommendations. Visualizations should be designed to support the story, not just display data, guiding the audience's attention to key points. By combining data, visuals, and narrative, analysts can create impactful presentations that influence decisions and inspire change. This skill is increasingly vital for data professionals, as technical prowess alone is insufficient without the ability to communicate insights effectively. Reporting and dashboards. Reporting and dashboards are essential tools for disseminating data insights to stakeholders, enabling continuous monitoring and informed decision-making. Reports are typically static documents that provide a detailed, historical overview of specific metrics or performance, often generated on a regular schedule. They offer in-depth analysis and explanations, suitable for comprehensive reviews and archival purposes. Reports can range from simple summaries to complex documents with extensive textual analysis and multiple visualizations. They serve as a record of performance and a basis for strategic discussions, ensuring that all relevant information is captured and presented systematically. Dashboards, in contrast, are interactive visual displays that provide a real-time or near-real-time snapshot of key performance indicators, KPIs, and trends. They are designed for quick comprehension, allowing users to monitor performance at a glance and drill down into details as needed. Dashboards are highly customizable and often feature interactive elements like filters, sliders, and drill-through capabilities, empowering users to explore data independently. While reports offer depth, dashboards prioritize immediacy and interactivity, making them ideal for operational monitoring and quick decision support. Both reports and dashboards are critical components of a robust data analysis ecosystem, catering to different information needs and consumption patterns within an organization.